So in the previous lecture, we saw how to generate randomness. That was kind of the first magic. And today we're going to see the next magic, which is how to give a proof, to convince that something is true without giving any information whatsoever. So this is really similar to magicians, right? Where they prove to you they did something, they prove nothing about like how their magic works. So this is going to be zero knowledge proofs. Actually, I'm not going to only talk about zero knowledge proofs. I'm going to talk about zero knowledge proofs and their evolution, the evolution they caused for proofs in computer science. Okay, so what is zero knowledge? So zero knowledge proof is this magical object. It's a magical proof that reveals no information beyond the validity of the statement. Seem like magic at first, and it should seem like magic because actually zero knowledge proofs are impossible to achieve. And the reason they're impossible to achieve is mathematical concept. Okay, this is information. It's something we can get, something we learn. Its mere kind of existence is information. Now I can walk around with this kind of paper, and this is information from my perspective. So of course it's not really clear because I didn't define it. But essentially, when you reveal no information, I want to say you didn't learn anything, not even a piece of paper that kind of can be verified. So a piece of paper that can be verified, that's in my perspective, it's some knowledge. It's some kind of knowledge. So, of course you should think, yeah, this is magical because this thing actually doesn't exist.
Yeah, I'm sorry to interrupt so early on, but I think some people are having a little bit of an issue hearing you. So I don't know if there's anything that you could possibly do on your end for audio purposes, but if there is, that would be helpful.
Okay, so 1 second. Let me see here. There's ways.
Yeah, maybe you could either,
is this
oh,
better,
yeah.
By the way?
A lot better, yeah.
Okay, great. Okay, but is this good or still not good?
It's good.
Is it okay? Okay.
Yeah, no,
sorry
a
about
lot
that.
better.
Okay, great. Thanks, Max. Okay, so as we said, and thank you, Jess, for the interruption. So as we said, constructing zero knowledge proof is impossible because this piece of paper on its own is some kind of information. So how did they do it? The way they did it is by changing the model. So rather than thinking of proofs as just kind of a written paper with a proof, which is the way we thought about proofs for thousands of years, started from kind of ancient Greeks who studied the notion of proofs. To obtain zero knowledge proof, the way they did it is by considering the model of interactive proofs. So what is an interactive proof? Interactive proof, it's not just a proof that we send out there, we put out there. Rather, it's an interactive process with a specific verifier. So let's say I know that Jess wants to verify my proof. I'm going to send her a message. Jess may send me back a question. I give her a message, and so on and so forth. It's a kind of an interactive process. And actually, what gives interactive proofs their power is the fact that the verifier is randomized. Okay, so it's allowed to toss coins. And moreover, I don't require kind of completeness and soundness to hold with probability 1 or probability 0. Rather, I allow some failure. So in other words, if X is in the language, I'm okay if you will reject, you won't output 1 always, but almost always, with probability, let's say 2/3. And for soundness, I'm not requiring that if X is not in the language, there is no accepting proof whatsoever. Rather, I'm saying that if X is not in the language, any cheating prover will convince the verifier with small probability. Let's say probability 1/3. And if you're kind of curious, why did I choose 1/3 and 2/3? What's magical about these numbers? The answer is nothing is magical. These can be amplified. So they're kind of arbitrary. The only thing that's important is that I have kind of a gap between the completeness and the soundness. And the reason why that's the only thing is important, what I can do is I can run this interactive proof, let's say k times. And then in the completeness case, I expect to, with very high probability, I expect to accept close to 2/3. And in the soundness, with very high probability, I won't accept much more than 1/3. So I can say, for example, let's do it k times, and let's think of half as the midpoint. If more than half are accepted, I'm going to accept, and if less than half, I'm going to reject. And by the soundness, because if X is not in the language, each kind of iteration, is going to be accepted only with probability third by kind of a standard Chernoff bound. I'm going to accept with exponentially small probability in the number of repetitions. Okay, but for those who not familiar with Chernoff bounds or with kind of concentration bounds, it's okay. You can think of completeness close to 1 and soundness close to 0. Okay, for simplicity.
I have a question.
Okay, so yes.
Is this kind of the same definition of how we define BPP?
Exactly. So right. So BPP exactly. So BPP can also be defined in this way, right? With third and 2/3, and then you just repeat. It's very similar. Exactly right. Thank you. Yeah, that's a good comment. Okay. So in this model, that's the model where interactive proofs where zero knowledge was suggested, and it was proven that indeed, this is kind of really amazing. Any statement that has a classical proof also has a zero knowledge interactive proof under a cryptographic assumption, assuming one-way functions exist. If you remember from last lecture, we talked about one-way functions. If you don't remember, we'll get to it. Okay, but the point to think about is every statement has a zero knowledge proof. And note that I did not define zero knowledge proof yet, but let me actually give you a very kind of nice illustration. So maybe still, you feel a little confused about how we construct these zero knowledge proofs. So let me give you a demonstration of how I'm going to construct it. I need to find 2 pens. Okay, here we go. So I'm going to give you zero knowledge proof. I have here 2 pens. They're different, but suppose you can't see the difference between them. Okay, I'm going to prove to you that they're different, but I'm not going to tell you how they're different. Actually, you're going to have no information about how or why they're different, but you will be convinced that they're different. Okay, zero knowledge proof. Here's how I'm going to do it. I have these 2 pens. I'm going to give them to Maxwell. Now I'm going to turn around. Maxwell's going to choose. I'm going to tell him this is pen A and this is pen B. Okay? I'm going to turn around. Now Maxwell will choose. Either he'll keep them on the same hands, this A and this B, or he'll switch. Okay, but Maxwell knows which is A and which is B because he knows if he switched or not. I don't know if he switched or not because I turned over. When he's ready, I'm going to come and I'm going to tell him which is A and which is B. Now, if they were the same, there's no way, I have no idea what is A. There's no way I can know what A and B are. So I'm going to fill with probability half. But if they are not the same, I'm going to always succeed because I know which one is A and which one is B. So I'm going to be correct. And as I said before, if probability half doesn't convince you enough, let's repeat it 100 times. So, again, I'm going to give you guys the pens. I'm going to turn over. You're going to decide if to switch the order or not. And I'm going to guess correctly every single time. And if I guess correctly every single time, then you should be convinced that I know that they're indeed different. But did you learn anything about why they're different? No, because I didn't give you any information. You knew if you changed the order or not. Okay, so this is really a zero knowledge proof. Okay, so even though in the beginning this seems like a very magical concept, you see that if kind of you change the definition a little bit, change the model a little bit, all of a sudden you can do it. And this is kind of indeed the basic idea behind zero knowledge. Note that you guys are the verifier, used randomness. Okay, so with probability half you switch, with probability half you didn't switch. This randomness is essential, and you'll see a homework assignment corresponding about this. Okay. Actually, to obtain general zero knowledge, the zero knowledge proof, we'll see to obtain general zero knowledge proof, also the prover needs to be randomized. And we'll see that as we go along. Okay. So I'm talking about zero knowledge, but we need to define, what does it mean to be zero knowledge? How would we define zero knowledge? So let's see. When you, the verifier, you come, you interact. At the end of the day, what do you get from me? Some transcript. Okay, you send message, I give you message. What information do you have? The transcript. What does it mean to be zero knowledge? It means that this transcript actually could have been simulated without knowing anything, without knowing, just with knowing the statement. So formally, the definition is this proof system is zero knowledge if there exists a PPT algorithm S, it's called like a simulator, if this algorithm can simulate this transcript. So I'll denote by PVX, this is a transcript corresponding to the statement X, and this transcript is zero knowledge if the simulator, who gets only the statement, he has no idea what the witness is, he doesn't know why the pens are different, he doesn't know what the NP witness is, but nevertheless, he could simulate this transcript efficiently. And what do I mean by simulate? I want to say that the simulated transcript and the actual transcript, they look the same. And as we'll see, by what do I mean by look the same? I don't mean that their distribution is identical. Rather, the same as what we saw at previous lecture, I mean that these distributions cannot be distinguished by polynomial time algorithms. So these two distributions are computational indistinguishable. Okay. So it's not the same distribution, but they're computationally indistinguishable. Okay. So again, if I can simulate efficiently this transcript, it means that, or something that looks like this transcript, it means that a polynomial time adversary looking at this cannot learn anything. Any questions so far? Okay. So even though I don't have much time, it's only an hour and a half, I'm gonna show you how to construct a zero knowledge proof for all of NP. Okay, not just in this toy example that I had, but actually I'm gonna show you how to construct a zero knowledge proof for all of NP. And what I like about this is, first, it's beautiful, but also it kind of builds upon things that we saw in the first lecture, which I think will be nice. Okay, so to construct a zero knowledge proof for all of NP, it's enough to construct a zero knowledge proof for an NP complete language. Okay, because if you have any other NP language, you can convert it to the NP complete and prove there. So it's enough to construct it for the NP complete. The NP complete language that we're going to use is graph 3-color. So the input, the statements are graphs, and they're in the language. So a graph I denoted by set of vertices V, set of edges E, and it's in the language. If the vertices V can be colored by 3 colors, I'll call them 1, 2, and 3, such that no two adjacent vertices, no two vertices in E, in the set of edges, have the same color. Okay, that's the language, that's the NP complete language. And I'm going to prove to you that I know coloring, but I'm not going to tell you anything about the coloring. Okay, so here's my graph G. I have a coloring. I want to convince you that I have a coloring, but I'm not going to tell you anything. I want you to learn nothing about my coloring is. So here's how I'm going to do it. First, I have my coloring. The first thing I'm going to do, I'm going to permute the coloring. I'm going to permute the color. So in other words, I have coloring 1, 2, 3. I'm just going to permute it. So 1 is going to be another random color, 2 is going to be another random color, and 3. So now each node I is colored in a fresh color. Okay, so I'm going to randomly permute the coloring that I have. And what I'm going to do, so let me first give you kind of a physical zero knowledge proof, and then we're going to make it kind of cryptographic. So the first thing I'm going to do is I'm going to give you locked boxes. Soon we're going to use cryptography to get rid of these boxes. But I'm going to give you a lockbox. You won't have the keys. Lockboxes with the name of the coloring. So in the first box, I put color 1. In the second box, I put like a little note saying color 2. Up to the last box, I put a note color in. And I give you these boxes. I'm not giving you the keys. You can't open the keys, so you can't find the colors. It's just an opaque box. You learn nothing so far. Then you come to me and you say, okay, I want you to open, you choose a random edge, ij, and you ask me, I want you to open the locked box number I and locked box number j, in which case I do. So I'm going to give you the keys for these two safes or locked boxes. And you're going to accept if what you see there is two legal colors that are different. Okay. Any questions about the protocol? About the... Okay. So now two questions. A, why is this even sound? Forget about zero knowledge. Why is it? So of course, if I have a coloring, you'll accept my coloring because I'll put the color, I'll permute it, I'll put it in the box. You'll give me a random edge, and when you open the safe, you'll see two different. If it's a legal coloring, you'll see two different colorings of numbers one, two, or three. So you're going to accept me. What about if it's not? If the graph is not three colorable? So if the graph is not three colorable, what I put in the safe is not a valid coloring because there is no valid coloring. The fact that it's not a valid coloring, it means that there exists some edge, ij, that if you open these two safes, you're going to get either the same color or an illegal color. I don't know, color number 4. So now, if by chance, with probability, 1 over size of e, you ask that color, I'm going to get rejected. So I'm going to be rejected with probably at least 1 over e. Now, 1 over e, you may think it's pathetic, it's not really good enough. That's right. Just repeat it many times. So repeat it much more than, e times, million. And now, if every time I convince you, then you should be convinced that, I have the coloring. Okay, so this is soundness. What about zero knowledge? Why is this zero knowledge? So I'm going to simulate. I'm going to show you that I can simulate this without knowing anything. But actually, before I construct the simulator, let's think together. What did you learn? You're the verifier. What did you learn? You got these safes. That's nothing. It's opaque boxes. And then you got I opened 2 of them. But what's in there? Just 2 random colors. Has nothing to do with the coloring. You just see, no matter which coloring I had, what you see is just 2 random colors. Okay, I can simulate that, 2 random colors. You learn nothing. Okay, so let's do this formally. What would the simulator do? So what he will do is he will guess what the verifier's edge is. So first he chooses randomly the edge. He doesn't know a coloring, right? So the simulator, he just knows the graph. He has no idea if it's colorable or not. He does not know the coloring. But here's how he generates a transcript that looks like the transcript of the honest prover. He will first simulate the verifier's random edge. So he's going to choose a random edge and first kind of decide on the verifier's message. Now that he chose that, he doesn't care what he puts in all the other boxes except for box I and J because they're never going to be opened. So he puts nothing in there. The only thing he does is he puts in box I and box J. So now he chooses at random 2 different colors and puts 2 different colors, valid colors, between 1 and 3. Puts one of them in safe 1, in safe I, and the other in safe J. And he gives you the keys. It looks exactly like the real execution. And yet, the simulator, generated this without knowing a color. So these 2 are actually identically distributed, and I didn't even know a color. So of course, you didn't learn anything, because that's all you learned, what I just gave you, which could be generated without knowing anything. Any questions?
I was wondering, is this the same situation as the one-time count that we can only take this transcript one time but not simulating the same situation for multiple times?
So you're asking, okay, good. Okay, that's a very good question. What you're saying is, let me make sure I understand your question. From my understanding, you're saying, yeah, well, when you do it once, it's zero knowledge. But now when you do it again, it's not going to be zero knowledge anymore because now I need to open more and more and more safe, and it's not going to be zero knowledge. But I can still make it zero knowledge. And the way I'm going to make it zero knowledge is next time when I execute it, I'm going to re-randomize my colors yet again. So I'm not going to use the same randomized colors. So me as a prover, we do it once. I randomize my colors. I put them in the lock boxes. You get one edge. You give me one edge. I open these two. And then you say, okay, but still it may not be three colorable because the soundness is so small. Let's do it again. I said, sure, no problem. I'm going to give you new boxes. And what I put in there is my colors, but re-randomize yet again. And then you choose an edge, and you'll still get two random colors that are distinct. And then you want to do it again? Sure. New boxes, new re-randomization. And I'm going to do it every time. I'm going to re-randomize my coloring. So at the end of the day, what you'll get is, let's say, K execution. But each time what you'll see is just two random distinct colors, two independent. So you didn't learn anything. That's a very good question. It's a very good question, and it's a good analogy to the one-time pad. But because it's like here we're doing it with a new pad each time. That's kind of the difference.
Right.
Okay,
Yes.
because I'm using new randomization.
Yes, but I was wondering, like, since we only have three colors, is that, can the eavesdropper just like simulate all situations very easily, or that's not possible?
So you mean, okay, so so you're still talking about zero knowledge, right? Not soundness. Yeah, so I want to say that I can still, so here's how it's gonna be zero knowledge, even if you do this sequentially K times. And the way I'm gonna simulate it K times is each time I'm gonna guess your edge, I'm gonna put, all the boxes empty except for the two boxes. So I'm gonna guess an IJ, I'm gonna leave all the boxes empty except for boxes I and J where I'm gonna put random distinct colors. And then I'm gonna open them. And then again, new boxes, choose new IJ, put new random distinct colors in the new IJs and open. And then again, I'm just going to do this over and over again. I can repeat it. I can simulate this as many times as you want.
Right.
So I can even simulate the repeated version. Yes, and that's important because it turns out that zero knowledge is closed under sequential composition. So if you have a zero knowledge protocol and you compose it sequentially many, many times, it's still zero knowledge. Okay, and that we need that because I'm sure, like here, I just showed zero knowledge once, but what if we do many, many times? It's still zero knowledge. By the way, as a side note, if we do it in parallel, it's not necessarily zero knowledge anymore. But, so if you have a zero knowledge protocol and you compose it in parallel, you may ruin the zero knowledge property. So but that's a side note. Okay, so one more. First of all, any other questions?
There's a question in chat. I think you sort of just touched on it, but the question is if it's re-randomized every time, is the distribution still going to be similar enough to the real proof?
Yeah, so it's going to be re-randomized every time, and in the real proof, I'm going to re-randomize every single time, and the simulator will, of course, that's the only thing you can do is re-randomize every single time. So yes, also in the original proof, if you do it sequentially many times, each time I'm going to re-randomize my colors. Any other questions? Or did that answer your question?
Yeah.
Okay. So, assuming there's no other question, is there another question? Just want to make sure I didn't miss.
There's nothing in the chat.
Okay. So far I just showed you how to simulate a transcript, assuming you're talking with an honest verifier. But I want to claim that this protocol is also zero knowledge, even if the verifier here is malicious. So even if he always uses, let's say, the same IJ, or he chooses the IJ, I don't know, as a function of the date or whatever. Okay, it's still zero knowledge. And that's going to be one of your homework assignments. Okay, so the next thing so far I showed you how to do zero knowledge, but it's assumed you have these safes and to go and get the safes and so on. Now I want to show you how I can implement these safes by using cryptography. And the primitive that implements a digital safe in cryptography is what's called a commitment scheme. So what is a commitment scheme? A commitment scheme is a randomized algorithm. We denote by COM for commitment, and it has two properties. So COM is an algorithm, and it has two properties, hiding and binding. The hiding says that if you take for any two messages n and n prime, in our context, these are colors. So for any two colors or messages, m and n prime, the commitment of m looks the same as the commitment of m prime. So in other words, if I commit the color 1 or color 2, if you see this random variable with randomness r, it looks the same. It's not necessarily the same. These distributions may not be the same, but they're computational indistinguishable. They're the same. They look the same in the eyes of a PPT machine. So that's the hiding. In that sense, they're opaque, like the safe. Okay, if I give you the commitment, you can't see anything. The next thing I need is also binding, that I can't put commitment and then change what's inside afterwards. Once it's there, it's there. And the binding says that for any, once you set the commitments, so a commitment cannot be opened to two different messages. So there does not exist a message with randomness, a message m and randomness r, and another message m prime and randomness r prime, such that the commitments are the same. So any commitment, there's only one message and randomness that can open that commitment. Okay, so you cannot generate a commitment and open it, both to message n and to message m prime, because such m and m prime do not exist. Okay, so this essentially means this commitment, you can think of it as a safe, it's high, and is you can open in two different ways. And the key to the safe is the randomness. Randomness, you check that this commitment function applied on the message, and the randomness is indeed the value, that the name of the value of the box. Any questions about the definition of a commitment scheme? Okay, so now what I want to show you is how to use what we learned about last lecture to actually construct a commitment scheme. And here is, first, before I show you how to construct it, let's go back to our zero knowledge proof and get rid of these physical boxes. Instead of the physical boxes, what we're going to have is the first message is just going to be commitment to C1 using randomness. I didn't write the randomness, but randomness R1, and so on and so forth, up to commitment of color N using randomness Rn. Okay, so in other words, what the prover does is, as before, he randomly permutes the coloring. He randomly chooses n randomness, R1 up to Rn, and computes commitment of C1 with R1 up to commitment Cn with Rn, and he sends these commitments as like a cryptographic analog to the digital safes. Then the verifier chooses a random edge, and he reveals his coloring by giving the coloring and the randomnesses that he used to generate these commitments. And what the verifier checks is that these colorings are distinct and valid, and that Ci with randomness I corresponds to the ith commitment. Okay, so this is the actual protocol. So now you know how to construct a zero knowledge proof for L of NP, assuming you know how to construct a commitment. And that's what I'm going to show you next, how to construct a commitment from one-way function. This is where the one-way functions are used. So far, I told you one-way function, we didn't use one-way functions. But to actually construct this commitment, I'm going to use one-way functions. Okay. Any questions so far?
Yes. So I was wondering, since the verifier only needs to verify that the two colors of one edge are different, I guess on the last step, when we reveal the colors, can we just send the commitment instead of the actual colors?
So, at the end of the day, the verifier needs to check that the colors are distinct, that what's in the commitment. So think of these commitments as safes again, and what he needs to check is what's in these safes or what's committed in the commitment are colors that are valid and distinct. So we need to give him these colors in order to verify the proof. So we need to give him these colors that we must do. So we have to send him the colors. But we also need to convince him that these are the colors that are in these safes, that these are the colors that are committed to. And the way we convince him that these are the colors that are committed to is by giving him the randomness. And once he has the randomness, he can recompute on his own the commitment. So he can apply on his own this commitment algorithm on CI and RI and see that it corresponds to the value here.
That makes sense. Yes. Thank you.
Great. Okay, thanks for the question. Any other questions? Okay. So now I want to show you how to compute the commitment function. So how to implement that. And this, as I said, it's going to use the ideas we talked about last lecture. And it's going to use a one-way function. And the commitment is so simple. It's really, really simple. So actually, for simplicity, I'm not going to assume a one-way function. Rather, I'm going to assume an injective one-way function. Even though we know how to construct commitments from one-way function, let me construct it from injective one-way function. And here's my construction. Choose your favorite injective one-way function. And remember, we said that every one-way function has a hardcore predicate. So let P be a hardcore predicate corresponding to this one-way function. And now here's the commitment. The commitment is a function. It takes a bit B. So we're going to commit bit by bit. I know that coloring is not bits, it's 1, 2, 3. So in code, each coloring is 2 bits. And when you commit bit by bit. Okay, so let me tell you how to commit to a bit B with randomness R. The way I'm going to do it, I'm going to compute the one-way function applied to R. The committer is going to be the one-way function f applied to R. And then I'm going to mask my bit B using the hardcore predicate applied to R. So really what I'm going to give you is the bit B with a kind of a one-time pad of the bit B. I'm going to encrypt the bit B with the key, which is the hardcore predicate applied to R. Okay, so P of R is my key, and I'm going to use that to encrypt the bit B. And now the point is, let's skip the binding for a second. The reason it's hiding, I want to say first, you don't learn anything about the bit B. Why? Because even if you see f of R, which you do, the hardcore predicate looks random. That's the definition of a hardcore predicate. That's precisely the definition. So the hardcore predicate is really a good key. It looks like a random key. And therefore, it really masks the bit. Okay, so it's a good mask, it hides the bit. By the way, no, if I commit to 0 with randomness 1, and then I commit to 0 with randomness 2, and then I commit to 0 with randomness 3, they all look random. You can't see that I committed to the same thing. You have no idea because each one is, f of R1 with the hardcore predicate on R1, which looks random, and you have no idea if I XORed it with 0 or 1. It just looks random. So you really get the hiding property we want. Moreover, it's also binding, and the binding is really statistical. It's really binding, as we said, because because F is injective, there's only one R that you can give that, well, of course, when you apply F on it, you'll get this value because it's injective. And so there's only one R that I'm going to accept, and the bit B that I'm going to accept is going to be P of R XORed with the second element. So it's really a binding. So it's information theoretical binding. Okay, once you have this pair, there's only one bit B and randomness that you can give that will correspond to this pair. And the hiding, on the other hand, is computational. So only for in the eyes of a polynomial time adversary, B is hidden. But it's not really hidden. If you're all powerful, you can find R, you can compute the hardcore predicate and find B. And that's why in the zero knowledge protocol I gave you, it's not really zero knowledge against any adversary. It's zero knowledge only against PPT adversary. So only PPT algorithms don't learn anything. Okay, nice. In this, my simulator is gonna, commit not a valid coloring, and I'm assuming that you can't distinguish between these commitments. Okay, so the zero knowledge is only computational, but the binding and hence soundness is statistical. Okay, questions? Any questions about this? Okay, so that's it. Oh yeah, go ahead.
Yeah, sorry. I still don't completely understand the revealing process. Like someone has chosen like I and J, and you give them CI, CJ, and like RI and RJ. But like, isn't it that you can choose like fake CI, CJ, and like choose some RI prime and RJ prime so that you'll still get a com of CI and RI? I mean,
okay,
how do you, yeah.
Yeah, okay, so actually there's two things I want to say. First of all, in the definition of commitment, I don't necessarily need the randomness to be unique. I just want to say that once I committed to, so let's go back for a second here, here. Once I send these commitments and you ask to reveal kind of the commitment I and J, there's only one CI. I can't reveal in a way that's accepting to both CI and CI prime. Okay, just to one CI. And the reason is, so it's not required that you can reveal with CI with a unique RI. Maybe there's many RIs, maybe there's many randomnesses that reveal to the same CI. The randomness does not need to be unique, but the CI, because the CI is what we're committing to. The coloring, you can't kind of open to two different colors. Okay.
Yeah, exactly. My question is that how do you convince a person that these are the real CI and CJ?
Good. Okay, great. So here's how. So suppose that the coloring is just a bit for a second, okay, for simplicity. Suppose the coloring is a bit. Now, so what sits in the commitment one? What sits there? Well, what is the commitment, right? It's a one-way function. So I choose a random R, I put a one-way function, apply to R, and then I give this as part of the commitment, and I also give the hardcore predicate applied to R, XORed with my color. Again, assuming the color is a bit for simplicity. Now I want to say there's no way you can open to a different B. Now let's say you committed to B, but you want to open to B prime. Good luck. How are you going to open to B prime? Which randomness are you going to give? If you don't give the same randomness R here, I'm going to reject you. Because with the verifier, you give him an R, the first thing the verifier does is he computes F on the R you gave him, and he's going to check that it's consistent with this value here. And if it's not consistent, he's going to reject. So the first thing the verifier checks is that the R is indeed the R you use, because it's injective. The only R that's accepted is this same R that you used. And then what he's gonna do, you claim to be prime. He's gonna check. Okay, let me check I'm gonna compute the hardcore predicate here, and I'm gonna check if your B prime is consistent. So I'm gonna compute the P of R. I'm gonna XOR it with the second element here, this bit, and I'm gonna see if I got the B prime that you claimed. And the only way I'm gonna get the only way you're gonna accept me if you gave me the correct R and the correct B. Otherwise, I'm gonna reject you. So
Yeah.
that's why it's binding. Is that helpful?
Yes, yes, completely. Thank you.
Great.
And just one other question.
Yes.
The verifier has the P function too, right? It has both F and P.
Yes, exactly.
I mean,
F is
we
efficient to
discussed.
compute. Exactly. F is efficient to compute. P is efficient to compute. And I assume both the verifier and the prover have access to these. These are fixed functions. Everybody knows these functions.
Great. Thank you.
Yes.
Thank you.
Thank you. Thanks for the clarification questions. Any other questions? Okay. So what did we see so far? We saw how to construct zero knowledge proof for all of NP, assuming a commitment, and we saw how to construct commitment, assuming injective only functions. So we really now are magicians. You can prove that any statement is zero knowledge to anyone. Okay, so congratulations, you joined the Magic Club. Now what I want to do in the remaining of the lecture, assuming, so now I'm going to shift gears. Are there any questions before I shift gears? Okay, so I want to shift gears and tell you a really amazing story of what this zero knowledge proofs, its greater contribution to theory of computation. And in particular, it really changed the way we think about proofs. And so now what I want to tell you a little about is how it contributed to the evolution of proofs in computer science. So now let's say I don't care about zero knowledge anymore. Okay, I don't care about hiding at all. Okay. Interactive proofs is a very interesting proof model. And the reason it is so interesting, it turns out that interactive proofs are much more efficient than classical proofs. What do I mean? So a classical proof is just kind of a piece of paper, right? And it turns out that generally speaking, classical proofs can be very, very, very long. Okay, so suppose I want to prove to you, I have a Turing machine, I want to prove to you that this Turing machine on input X outputs 1 within T time steps. I have no idea how to give you succinct proof of that. I think the only way I know how to do it is just kind of running showing the tableau of the Turing machine, and you verify it. It'll take you time T. I don't know how to convince you, efficient verifier, that this very long, inefficient computation is correct. Okay. However, what turns out that I can do that for at least some Turing machines, for some computations, using interactive proofs. And let me give you kind of one really nice example that may shed some light on why interactive proofs are so powerful. So look at the example of chess. Okay, so suppose now I have a configuration of the board, of a chessboard, and I want to prove to you that the black player has a winning strategy. Now, how do I do that using classical proof? I have no idea. I mean, the only way I know how to do that is to say, well, no matter which move the white does, the black player has a move such that no matter which step move the white does, the black player has a move such that at the end, in all these, final configurations, the black player wins. But if I give you such a proof, it's going to blow up exponentially very, very fast. Turns out, using interactive proof, I can do that very efficiently. And I'm not going to prove to you how. It's actually a complicated and very beautiful proof. But essentially, think about it, okay, this is not convincing, but let's say I'm a black player, I'm going to play with you. I'm going to play with any grandmaster, and I'm going to always win. So maybe that's somewhat convincing, and that's very efficient, right? We just play kind of one game. So that's kind of of course, it doesn't, the fact that I'm winning a grandmaster doesn't mean I'm going to win any grandmaster or any player, but that's kind of the intuition of why interaction is helpful. But it turns out that actually this can be formalized, this intuition can be formalized, And it was done by this beautiful works of Nun, Fotno, Karloff, and Nissan and Shamir that showed that the correctness of any computation can be proved such that the time to verify this proof is proportional to the space of the computation. So if you have a computation that takes a lot of time, but doesn't require much space, interactive proofs can be very efficient. The runtime of the verifier depends on the space, not on the time. So if you think of space efficient computations, these can be proved very efficiently using an interactive proof. And we don't know how to do this using a classical proof. Not only don't know, we believe it's impossible using a classical proof. So now, this model became really interesting. Forget about zero knowledge. Who cares about zero knowledge? Now all of a sudden you can prove things very efficiently, which you couldn't prove before. So this kind of, so this theorem is known as the IP equals P-space theorem. IP stands for interactive proof. And we got from this that computation that requires succinct space have succinct interactive proofs. Okay, so this was great. But then, shortly after this interactive proof model was proposed, for the sake of zero knowledge, a new model was proposed. And that's called a multi-prover interactive proof. It again was motivated.
Before you move on, can I ask a question?
Of course.
Yes, so I was wondering, is the interactive proof also randomized in this case?
Yes. Okay, the interactive proof, the verifier is randomized. The prover is not randomized, but the verifier is randomized. And let me tell you, if the verifier is not randomized, this interactive proof has no power. It loses all its power, and that's part of the homework assignment, okay? Interactive proof with a deterministic verifier is like a non-interactive proof. It goes back to the classical setting. So really the power of interactive proofs comes from the fact that the verifier is randomized. And also here, to prove this, you use randomness. That's crucial, yes.
Right.
Okay.
I guess I'm just a bit, I find it a bit difficult to wrap my head around the fact that IP equals P-space, because when we think of P-space, that's deterministic, isn't it?
Right. So the prover will be deterministic. Okay, the prover answers in a deterministic way depending on his computation. But the verifier will be randomized. And essentially you can think of it, the verifier chooses randomly which part of the computation to focus on. So the verifier can't check the entire computation. That's too much, of course. So essentially the way this works is the verifier is going to check randomly. Let me check this part of the computation. Let me check this part of the computation. But of course that also was not enough, because if he checks just little parts of the computation, he may not check where the hard part is. So they use kind of these error correcting codes to be able to check in random places that are they first propagate the error everywhere, and then they check random places. That's, I think, the intuition for these protocols. But again, it's kind of complicated. Yeah.
It's just that from the first side, it looks like P-space is much more powerful, because with that case, you don't really have limited time.
Right. Actually, you're right. So it was very surprising result that you can in an interactive proof you can prove all of P-space. That was very surprising, actually. So I agree, it is pretty, because you're saying, but don't forget that in IP, the prover is very powerful too. So it's not like nobody's doing the computation. You have a prover who's doing this computation. He works very hard in these IP, in these IP protocols. But still, the fact that he can prove it to a very efficient verifier is pretty remarkable. It's really astonishing. So it's pretty magical. I wish I had another lecture to show you how this protocol, because it's so beautiful in my opinion. Okay. So back to where we were. So shortly after the interactive proof model was introduced, more powerful model was introduced, and that's the multi-prover interactive proof. Before I define this model, let me just say, it was again, the reason it was put forth is the motivation was again zero knowledge. And if you remember the protocol I gave you before, it was only computationally zero knowledge. It was only a PPT adversary cannot learn anything. But actually the commitment, the coloring was sitting there. It just hard, it looks random, but if you're all powerful and you can invert the one-way function, if you can break the commitment, you can see the coloring. So it was only computational zero knowledge. In this work, what they wanted to do is to get perfect zero knowledge, like to be able to simulate it perfectly, with not relying on one-way functions, or they wanted to say that this transcript can be simulated perfectly. So the output of the simulator has the same distribution as the output of the real transcript. And to get that, they couldn't do it using interactive proofs, so they changed the model. This is, by the way, typical crypto. Things are impossible, but they're never really impossible. You just need to change the model, okay? This is kind of these magic turns and kind of is going on everywhere in cryptography. It's really, really beautiful. Okay, so what is this model? In this model, they consider two provers, not just one. So I have a verifier interacting with two provers. As before, the verifier tosses coins. He sends messages, queries, questions, query 1 and query 2 to provers P1 and P2, and they give back answers, A1 and A2. This is the model. But what's important, and this is very crucial for this model, is that the provers P1 and P2 cannot interact. So they may interact before the protocol began, but then we have a brick wall between them. And only after they have this brick wall, then the verifier sends these two queries. Okay, so in other words, P1 cannot tell P2 what his query Q1 is, and vice versa. Okay, they sit in different rooms, they do not communicate. That's very important. And turns out that in this proof model, this proof model is extremely powerful. And what was shown is that actually any proof can be made exponentially shorter in this model. So in other words, if I have a proof of length big N, in this model, I can communicate only log n bits and convince you. So the verifier only needs to send log n bits to the provers, and he reads their answer, which are short, also log n bits, and he's convinced with reasonable probability. So that's pretty amazing. It's a very, now not only p-space, you can do non-deterministic exponential time, and the polynomial time verifier can verify this efficiently. So that's amazing. Kind of where does this power come from? This can be very surprising. So let me try to demystify this and try to tell you where the power of this proof system comes from. So I think a good analogy is think about these two provers as two different suspects. So they're trying to cheat, and I want to say they won't succeed in cheating. I'll be able to catch them very efficiently. Why is it so hard to cheat in this model? So think about suspects. Suppose someone, committed a crime. And now I have two suspects, two different rooms. It's very hard for them to cheat consistently. So they need to cheat, but they need to cheat consistently. Because I'm going to ask one suspect, one cheating prover, something, then I'm going to check his answers compared to the other cheating prover, and so on and so forth. So these consistency checks makes it much, much harder to cheat. Whereas if I have just one suspect, like in the IP setting, where I have just one prover, it's much harder to catch him. I mean, he can lie, and it's harder to catch the lie. But it's much harder to lie consistently when the two provers are not allowed to interact. And of course, I'm not going to give you the protocol here. It's very complicated. It's complicated, even more complicated than the IP equals p-space protocol. But essentially what's going on here is a bunch of consistency checks. It's really kind of similar to follows the intuition of the two suspects. Okay, so this is the multi-prover interactive proof setting. And let me say it a little more explicitly. So what we prove is that what is proven is that for any function f that is computable in time t, two provers can convince the verifier that the computation is correct, f was computed correctly, where the runtime of the verifier, or the communication complexity is only polylog t, actually it can be down to log t, and the verifier of course needs to read the input, but not much more than that. He runs in time the input length times polylog t. Actually, this can be even plus, and this can be order log t. It can be done really, really efficient. Okay, so it's already my time. I guess we have only 25 minutes left for the lecture. I'm wondering if you guys want a quick break before. Last time we gave kind of a break to maybe we should do breakout rooms for 5 minutes, just for a quick break, and then we'll continue. Does that sound good? Oh, I guess, do I need to do the breakout rooms, or? I don't see how to do it, actually.
Oh, actually, I can do breakout rooms this time.
Okay, so let's take a couple minutes break and reconvene, just to let you guys... But I'm here for questions. If anybody has questions and does not want to go to the breakout room, you can stay, you can ask me if you would like.
I do have a question.
Yes.
It was about the generating encoded messages longer than the original message.
Wait, again, can you say it again?
Oh, so it was about generating encoded messages longer than the original message.
What do you mean? When did we generate encoding method? Which, are you talking about the zero knowledge part, or are you talking about the after?
Well, this is from
maybe
last
I'll
lecture.
share screen
Sorry.
again, then you can tell me. Oh, sorry. Okay, you're going back to the previous lecture. Okay, yeah. So I'm not sure which. What do you mean generate encoded messages that are longer than the messages?
Can I share my screen?
Sure. Oh, I don't know. Jess needs to allow. Oh, you got it. Okay.
I was just thinking of how it'd be possible to make an encoded message longer than the original message, while maintaining
encoded.
maintaining the integrity.
So when you say encoding, what do you mean by encoding? You mean encrypting, or?
Oh, encrypted. Sorry, that's the
okay.
Wrong word.
Okay, so you're saying you want to encrypt the message in a way that, what do you mean that maintains the integrity?
As in makes it so it doesn't give up any information.
Oh, okay.
Even if
hides. Yeah. Oh, okay. Good. So you're asking, now I understand your question. You're asking, once we encrypt the message, do we necessarily need to make the encryption bigger than the message itself? That's your question.
Yeah.
Okay, good. So the answer is kind of yes. Okay, the short answer is yes. But it's yes if you want many times security. So for example, the one-time pad is an example where you don't increase the message length, right? You just take the message, you XOR with the key, and it's exact same length. So you don't increase it. But once you want many times security, then the answer is yes, you do need to increase. The encoded message becomes bigger. It doesn't need to increase by a lot. It increases by some security parameter. So in other words, if you have a message of arbitrary length, it can be huge or huge. I can encrypt it by, let's say it's big N bits. So I have some security parameter K, and I can take any message of length N can be as big as you want, and to encrypt it, the number of bits I use is N plus poly K, or plus K, So I can, the blow-up doesn't need to be huge, but there must be a blow-up. Okay, you can't encrypt without blowing up at all. And to see why that's the case, let me see if I have a quick explanation for why it must blow up. Or if anyone in the audience has a quick explanation, please unmute yourself and share.
So encryption has to be perfectly binding. So if you go to a shorter length than the number of preimages, like you can't find a unique preimage by decryption in some sense.
Right. But why can't it be the exact same length? Why can't you apply like a hard permutation kind of?
I guess, isn't it also true that each randomness, or maybe it's not true that each randomness has to go to a unique ciphertext?
Okay, so yes, okay, maybe this is maybe a good answer along with what Cody just said is okay, we know that encryption, to be really semantic secure, it needs to have randomness. And you can't take two different messages and randomness and take it to the same one, because then you can't decrypt. You don't know which one it started from. So for any message, so that's the answer. That's a formal answer at least. If you really want security, like semantic security, we know that encryptions need to be randomized, and moreover, the encryption function takes a message in randomness, and it has to be injected. It can't. So it can't take message one randomness one, message two randomness two to the same ciphertext, because then you can't decrypt. So that's kind of why things grow.
Oh yeah, thank you.
It's a good. Okay, so is everybody back or not yet? It looks like.
I'm sorry. I didn't actually initiate the breakout rooms, I don't think, because I thought that people might be interested in Grady's question.
Oh, okay, great. No. So then no. So let's. I don't know. So maybe we'll continue because we don't have much time. Not that I have too much more to say, but if people are okay, let's just move on and continue. Okay. So I don't have too much more to say. It's going to be quick from now. But okay. So what did we show? We talked about, there was zero knowledge. It motivated interactive proofs. Interactive proofs are amazing because they're very efficient. You can prove anything in p-space to using an interactive proof to a polynomial time verifier. But then we just saw there's a better, another model where if you assume you have two provers to your dispense, then it's really hard for them to cheat, which makes, and assuming they don't interact, that it's really hard for them to cheat. And you can make for any computation, any proof of exponential size, we have, or any proof of length n, we can prove it using a two-prover interactive proof where the length of the communication complexity is order log n. That's how you should think about it. And that's really amazing. But maybe you don't yet share my enthusiasm, why it's so amazing. So I'm going to convince you why it's so amazing. And I really believe that you're going to really be blown away next. Okay, so take this in. Okay. If the queries are so short, they're only log n bits, where n is the length of the proof. Here's another way. Second. Yeah. Here's another way to think about it. Maybe instead of interacting with the prover, think of the prover as giving you the entire database, which is for every possible query, he gives you an answer. So, there's order log n bits here. So there's like poly n possibilities. For each possible kind of query here, he'll give you all the possible answers. Now it's only polynomial in the length of the original proof. If the proof was of length n, and I said that the number of queries, that the length of the query is only log n. So the number of such queries is 2 to the order log n, which is poly n. So if the original proof that you needed to verify bit by bit by bit by bit and read all these bits, now I'm going to replace at least this prover by a database of size poly n, bigger than the original. It's poly n, but I'm going to replace the prover 1 with this database. And I'm going to do the same to prover 2. I can replace prover 2 with this database. So now what happens? I say, you know what? I don't need prover 1, prover 2. Just give me all the possible answers of prover 1. Give me all the possible answers of prover 2. Once you gave me all the possible answers, I can think of all this as a big proof. It's bigger than the original proof. So you can say, what did you do here? I start with a proof of length n. You made this part poly n. You made this part poly n. Now you're telling me I'm giving you a proof of huge length poly n. What's up with that? Here's what's up with that. This is the amazing thing about this proof. It can be verified. Let me go back. You can think of this proof, and it can be verified by reading only 2 blocks. 1 block here and 1 block here. And each block reads only order log n bits. So now, what is this proof? This is a very weird proof. If you think about it, all the proofs that we learned and loved for thousands of years, how do they work? You read 1 line, implies 1 line, implies 1 line. You read kind of line by line and verify like a compiler. Now I'm giving you a totally different way of thinking about proofs. Here's a proof, consists of these 2 databases, and just randomly select blocks to verify. You use coins to select which part of the proof you read. And you need to read only a very small part, log n part of this proof. And this just follows immediately from the multi-prover interactive proof. So this is what led to the notion of what's called probabilistically checkable proofs. The checkable proof is exactly a big proof, okay? And in a way that you don't need to verify this proof by reading line by line by line, like we verify, our proofs in our papers. Rather, you verify this by reading only a couple locations in this proof. And here's what's really mind-blowing. So there's been a lot of work on these probabilistically checkable proofs called PCP for short. And the latest and greatest about PCPs is the following. Any proof we can convert into a probabilistically checkable proof. We increase efficiently even. Okay, I can take a proof of length n. I can convert it to a bigger proof of length poly n. And this longer proof is probabilistically checkable in the following sense. I can read only 3 bits of the proof. 3 bits. And I can be convinced with probability at least 1/8. And if that's not good for you, repeat. But think about it. I can take a huge proof. I can read 3 locations and be somewhat convinced that the statement is correct. This is true for any NP. So any NP statement, any statement that has a poly-sized proof, I can encode it a little bigger in a way that can be verified by reading 3 locations with some constant probability. Okay, so, if you're not blown away by this, then, I find it I remember when I studied it, I was in grad school and I could not sleep at night. This is unbelievable. And now we think, why are we reading all these proofs so, meticulously. If we can only, if everybody can submit their papers to the conferences using a PCP, it would make our lives easier. Okay, but this is the notion of PCP. Any questions? Okay, so let me then. Oh yeah, sorry.
Oh, this is probably a bit vague, but to me it looks somewhat like you're doing actually a property testing of the database.
You know, you're totally right. This is actually a technically speaking, that's a little bit what we do. So just to demystify this a little bit, it will still be completely mystifiable, but just kind of what's going on here is we take, how do you construct a probabilistically checkable proof? In a very, very loosely speaking, the way we do this, we take the proof, we encode it kind of using a big error correcting code. And what this does for us is that if there was some inconsistency somewhere in this proof, it propagates this inconsistency everywhere. And so now what happens, either everywhere was correct or many places it's, you know, it's not correct. And now we just check kind of, we do property testings. We check, you know, small, so you can think about, you know, there's some property and we kind of check it kind of locally. That's very broadly, it's like high level what's going on here, how these PCPs are generated.
Thank you.
Any other questions? Okay, so let me kind of summarize quickly. So what did we talk about today? You know, we start with classical proofs. With these things, very little, even though classical proofs is what we, you know, was in our, what we had for thousands of years, you know, started in ancient Greece all the way till like mid 80s. That's what we had, classical proofs. Then the mid 80s, a big boom, people cared about crypto, about hiding, and came up with this notion of interactive proofs motivated by zero knowledge. Now all of a sudden, wow, things can be done much more efficiently. This is a very powerful proof system. It led to an even more powerful proof system, multi-prover interactive proofs, which led to PCPs, probability checkable proofs. And actually now there's even more I didn't have time to talk about, but there's interactive PCPs or interactive oracle proofs. And kind of this kind of evolution of proofs continues and continues. And what I want to tell you guys, especially as students who are interested in theory, and I want to kind of end with this, it's kind of a conceptual note for you guys. You know, theory is kind of course, it's based on fundamental math. And if you look at these protocols, the IP equals P space, or the, you know, the PCP, or the multi-prover, the MIP, and you look at it, it seemed like, wow, it's really very fundamental and basic kind of math, and there's no way it will ever be, I don't know, useful in reality. And actually, when I was a student at MIT, which was a long time ago, I remember, you know, reading about PCPs. I was really intrigued by it. And I remember people saying, oh, but these are never going to be used. You theorists sitting in your sandbox, theory sandbox, but, you know, doing these useless things. I want to say these things are extremely useful today. Actually, they're implemented. They're used a lot on the blockchain now, because, you know, on the blockchain, you want kind of short certificates that things are correct, and, you know, these PCPs can be used to generate these short certificates. I didn't tell you how, but, you know, there's ways of converting all these kind of beautiful models to kind of short certificates. And so, you know, these things are used, and it's kind of a really beautiful example of how very fundamental and basic theory is, you know, really useful. There's several, you know, startup companies now that are worth quite a bit, that are using these things. And so, you know, this is just kind of to end on a positive note, that, you know, there's a really beautiful interplay between theory and practice. And, you know, I think theory is a very, very valuable and interesting, both mathematically and just an interesting thing in, you know, reality, how these things are used. Okay, so that's all I wanted to say. There's 2 homework assignments that, you know, the you'll work on together with the TAs. One of them is about why, in interactive proofs, it's very important that the verifier is randomized. Why, if he's deterministic, kind of things collapse to the, standard non-interactive setting. And the other question, which is question number 2, which is much more involved, is in class we talked about honest like in today's lecture, we mainly talk about honest verifiers, zero knowledge. But I want to say you can simulate also malicious verifiers. So a malicious verifier whose goal is to just learn, that he's not following the protocol. He just wants his only goal. He doesn't care if the statement is correct or not. He just wants to learn information about your witness. That's kind of his goal. Even he does not learn anything. So, you'll show in the TA session that the protocol we showed for graph 3 coloring is also can be simulated even when the verifier is malicious. Okay, so that's it. I'll end here. Thank you very much, and I'm here for questions if you have any. So maybe I'll stop sharing the screen. So I see there's a lot of things in the chat, but I think at this point, there's no point in moderating the chat. But
I'm going to go ahead and turn off the recording too, just in case anyone feels more comfortable asking a question if it's not recorded.
Sure, of course. Yeah, please do. Yeah, so if you have any